On our previous lesson, we have learned angular momentum, which can be written with formula angular momentum that is equal to r radius vector r multiplied by momentum p. This is angular momentum, and torque or moment of force torque that can be written with formula r radius vector multiplied by force. This is angular momentum related to the point, and torque related to the point. Okay, let's find the first derivative. From angular momentum. Let's find first derivative. This is equal to derivative of this vector product. And this is equal to r by first derivative of radius vector by time multiplied by momentum plus cross product of radius vector r multiplied by derivative of momentum by time. Okay, so what can we say about these two terms, these two vector products? From kinematics, you can remember that this derivative is equal to vector of velocity. This is vector of velocity according to kinematics. And from dynamics, we can remember the second Newton's law of motion. And according to this, this derivative is equal to force. According to the second Newton's law of motion. So we can use this here and write that this is a force. Okay, so let's continue. This. Here we have velocity multiplied by momentum and plus radius vector r multiplied by force and from our one of our previous lessons, we can remember that momentum is equal to mass multiplied by multiplied by velocity. And it means that momentum has the same direction. Vector of momentum has the same direction as vector of velocity. And according to vector algebra, it means that this product, or modulus of this product, modulus of this vector product is equal to modulus of vector v, or absolute value of vector p, a vector of momentum, multiplied by sinus of 0, and this is equal to 0. This is equal to 0. So it means that this vector product is equal to 0. This is equal to 0. And from here we have this. But this vector product is the same as moment of force. This moment of force. This is moment of force. This is moment of force, and we have m here. We have m here. Hey, do you have any question? Do you have any questions? No questions. Okay, thank you. Thank you. So we can write short. We can write this in a short way. If I clean some unnecessary lines, and according to this, we have such equation of equation for dynamics of rotational motion. So we have this equation, or we have similar equation for rotation around the fixed axis. For rotation around the fixed axis, we have very similar equation. We have similar equation. We have very similar equation, but it is necessary to write this like this. Yes. So what do we have? We have equation of momentums, or equation that connect equation of rotational motion dynamics. Equation of rotational motion dynamics. Okay, so if you don't have any questions, let's continue. Let's continue this. Let's continue this. So if we have rotation of perfectly rigid body around the fixed axis, what can we do in this case? What can we do in this case? I'll draw the axis of rotation, which is signed by the radius of rotation, of some material point, radius of rotation, and angular velocity, omega is angular velocity. Here we have the right angle. So in this case, the direction of rotation can be shown with this arrow, and the direction of velocity is here. This is perpendicular to the screen, and it is from us to the screen. The direction of vector v. The direction of vector v is from us to the screen, and it is perpendicular. It is perpendicular to the screen. And it is also perpendicular to r and omega. So v is perpendicular to angular velocity, and v is perpendicular to r. And what can we say about angular momentum? With respect to with angular momentum related to axis z. Angular momentum related to axis z, to fixed axis. This is equal to r, according to our previous lecture. This is equal to r multiplied by p perpendicular to the screen, in this case. But we can say that in our case, in case of rotational motion of rigid body around a fixed axis, that p perpendicular is equal to p, and this is equal to mass of material point multiplied by vector of velocity. Mass is a constant. So it is scalar constant. It can be written outside the cross product. So we have r multiplied by v. And now it is necessary to remember kinematics. kinematics. According to kinematics, we have that V is equal to omega multiplied by R. Multiplied by R. Omega multiplied by R. So this will be M multiplied by vector product of R multiplied by omega multiplied by R. Multiplied by R. And the next step is to open this double cross product or double vector product. There is a formula. There is a formula in vector algebra. I'll write this formula. According to this formula, A multiplied by B multiplied by C this is the formula from vector algebra. And this is equal to B A C minus C A B So let's use this formula here. We will have M mass multiplied by angular velocity omega multiplied by R and R scalar product of or dot product of R and R, and minus R multiplied by R omega. Sorry, I have forgotten to write mass. In front of the R. I have forgotten to write this. And what can we say about these two terms? Let's try to remember. From vector algebra some properties of scalar product, and from this we have that dot product or scalar product of vectors A and B is equal to A B absolute value of A absolute value of B multiplied by cosine phi, where phi is the angle between vectors A and B. Phi is is the angle between vectors A and B. And according to this formula, we have that dot product of R and R is equal to modulus of R cosine, because R and R are the same vector. The angle will be zero. And from here we have that this is equal to R and R, and this is equal to R, and this is the same as squared R. Okay, and what about the second term? The second term R and omega. R and omega is equal to modulus of R, modulus of omega, multiplied by cosine, and according to the picture, we have the right angle 90 degrees, right angle between R and omega. So here we have 0, because cosine of 90 degrees is equal to 0. And it means that we have from here and from here, we have that we have m r to the power of 2 and multiplied by angular velocity. It is for one material point. It is for rotation of one material point around the fixed axis. Okay, and do you have any questions about this? I think minus means that there are no questions. Okay, so let's continue. And let's continue. And I will clean some unnecessary things. And I will leave only the final result. Only the final result that we need from here. Only the final result that we need to know. This is for one material point. And of course we can sign this material point as I. I is a number of material point, and from here we can write that this is equal to I z of I material point and multiplied by angular velocity. And what is IZI? This is a moment of inertia of material point. So IZI is equal to MI RI to the power of 2. And from here we can see that moment of inertia is an additive value. Additive value, it means that moment of inertia of the whole system is equal to the sum of moments of inertia of material points of this system. So we can write that moment of inertia moment of inertia related to an axis moment of inertia related to an axis is equal to is IZ, and this is equal to sum of and this is equal to MI RI to the power of 2. This is a moment of inertia related to an axis. Moment of inertia of some material system. A material system is a system of material points. System of material points is a material system. Is a material system. Oh, and we will see soon why do we need why we need this moment of inertia. And now it is necessary to say a few words. It is necessary to say a few words about about calculating of moment of inertia of perfectly rigid body. Perfectly rigid body consists of infinite number of material points. In this case, what can we do? We can choose infinitely small element of rigid body and calculate its moment of inertia. Infinitely small element has a moment of inertia r to the power of 2 multiplied by mass of infinitely small element, and this can be written if you remember from school the formula that density is equal to mass divided by volume. This is density of homogeneous body. Density of homogeneous body is equal to its mass divided by its volume. So from here from here we can write that this is equal to r to the power of 2 rho, where rho is density of rigid body, density of rigid body, and it is multiplied by dv. And from here we can calculate the moment of inertia of perfectly rigid body. It will be Iz is equal, which is equal to integral power of 2 dm, and this is equal to triple integral on the whole volume, triple integral of r to the power of 2 rho dv. The moment of inertia for perfectly rigid body. Moment of inertia related to an axis for perfectly rigid body. This can be calculated with this formula. Okay, do you have any questions? No questions. Okay, and let's try to use this formula to calculate moment of inertia, for example, for thin homogeneous rod. I will try to draw this. This is thin homogeneous rod. In this case, we have this is axis z. Here we have half of its length. L is the length of the rod. Here we have L. And mass is m. Okay, how to calculate its moment of inertia? For infinitely small element of this rod, it will be di is equal to r to the power of 2 dm, where dm is infinitely small element of this rod. We can choose this infinitely small element dm, and this distance is r. This distance is r. Distance between the axis of rotation and the infinitely small element dm. And it can be written in other way. It can be written as r to the power of 2 lambda dr. And what is lambda? Lambda is linear density. Linear density is for homogeneous body, for homogeneous thin rod, can be can be calculated as mass divided by length for homogeneous rod. So we can write that this is equal to m divided by L, mass divided by length, multiplied by squared r, and multiplied by dr. Multiplied by dr. And from here we can obtain that this is that moment of inertia is equal to integral from 0 to I z di, and this is equal to integral from minus L divided by 2 to L divided by 2. From left end of the rod to the right end of the rod. From left end to right end. Okay, and let's calculate this integral. It will be m divided by L, integral of minus L divided by 2 to L divided by 2 r squared dr. It will be m divided by L, and it will be r to the power of 3 divided by 3 from r equal to minus L divided by 2 to r equal to L divided by 2. And this is equal to m divided by 3L. And here we have L divided by 2 to the power of 3 minus L divided by 2 to the power of 3 to the power of 3. And from here we have m squared L divided by 12 divided by 12. Okay, do you have any questions about this? Moment of inertia of a thin homogeneous rod. Moment of inertia of thin homogeneous rod. No questions. Okay. If there are no questions, I will clean some place. On the screen. I'll clean some place and we have that we have this simple formula for moment of inertia of thin homogeneous rod. Moment of inertia of thin homogeneous rod. I will write this. Moment of inertia of a thin homogeneous rod. Of thin homogeneous rod. Of thin homogeneous rod. Thin homogeneous rod. So for in this case, we have ready to use formula. So we don't need we don't need to obtain this. We have ready to use formula for this moment of inertia. In the same way, or in similar way, we can find moment of inertia of homogeneous cylinder. Moment of inertia of a homogeneous cylinder. Homogeneous disk. Homogeneous disk. Homogeneous disk. Homogeneous disk. So let's write this. I'll show here the axis of rotation. axis of rotation is here. Here, the axis of rotation. This is cylinder. This is cylinder, and here I have. Here we have this, and axis of rotation. Axis of rotation is here, and this is z. This is z, and radius is r. Radius is r, and here it is necessary to make dash line. Dash line, because this line is hidden from us. This line is hidden from us. This line is hidden from us. So in this case, we have that I will show this formula without proof. This will be IZ is equal to m r to the power of 2 divided by 2. Okay, so do you have any questions about this? Do you have any questions? No questions. No questions. Okay. Okay, so thank you for this. We will continue. We will continue now. It is necessary to frame this in red, because it is also ready to use formula for us. And the next formula is moment of inertia. Moment of inertia. Moment of inertia of homogeneous ball. Related to an axis that passes through its center. Because it is important. It is important for moments of inertia. So it can be calculated by ready-to-use formula. That can be written as 2 divided by 5 m r to the power of 2. So and it is also framed with red. Okay, and what will we have to do? What will we have to do? If we have to calculate the moment of inertia of some rigid body, some rigid body, with center of mass that is here, center of mass, and let's imagine that we know moment of inertia related to the axis that passes through center of mass. So it will be, for example, z o. Let's imagine that we know that moment of inertia related to the axis ZO is equal to I0, or moment of inertia related to the axis Z0 is equal to I0. And if you want to calculate moment of inertia related to the axis Z, that is on distance d from initial axis. This is d. In this situation, we can use so-called parallel axis theorem. Parallel axis theorem. According to this, we have that moment of inertia related to axis z is equal to moment of inertia related to axis that passes through center of mass plus m multiplied by d to the power of 2. This is parallel axis theorem. It's a pity that we don't have enough time to prove this theorem. But if you are interested in, you can find this in the internet. And now we have to just learn and write this parallel axis theorem. Okay, and why do we need this moment of inertia? I have cleaned some necessary formula. Why do we need a moment of inertia? According to things that was written before, angular momentum can be written with moment of inertia according to this formula: Iz multiplied by angular velocity. I have forgotten to write this in frame. to write this in frame, because we need this. We need this. And if we use this, if we use this, if we use this, we can make substitution. We can make substitution, and we will obtain. We will obtain. We will obtain that this is equal to I first derivative of angular velocity, and this is equal to mz or as you can remember, this derivative is equal to angular acceleration. So we can write that this will be Iz multiplied by beta. Multiplied by beta. Multiplied by beta. And this is equation. Equation of rotational motion, equation of dynamics, rotational motion of a rigid body around a fixed axis. Around a fixed axis. So this can be written with such formula. And from here we have that if moment of force or torque, if torque is equal to zero, that if torque is equal to zero, we have that if torque is equal to zero, we will have law of conservation of angular momentum. Law of conservation of angular momentum. Law of conservation of angular momentum. According to this law, if moment of internal forces, or external moment of external forces, if moment of sum of external forces is equal to 0, we will have that L z is equal to z omega, and this is equal to constant. This is equal to constant. According to these laws of dynamics, because because here we have first derivative of angular momentum, and if first derivative is equal to 0, it means that the function is a constant. If derivative is equal to 0, the function is constant. Okay, a law of conservation of angular momentum. And now it is necessary to say a few words about gyroscope. What is gyroscope? A gyroscope is a massive rigid body, that rotates around fixed axis, and imagine that we have rigid body that rotates with angular momentum L, and it rotates with angular velocity omega, and let's imagine that we impressed a moment of force, or we impressed a torque, M. That we impressed torque M. Let's impress torque M upon this rigid body. What will happen? According to our intuition, according to the direction of this moment, axis of rotation will rotate in this direction, but it is not correct. Our intuition is not correct. Why? Why is it so? It is because this equation of dynamics of rotational motion. It is because of this. is because of this. So I have forgotten to write vectors above the angular momentum. According to this, vector dl, increase of angular momentum, has the same direction as m. So it means that we will have something like this. We will have something like this. This second vector is L plus dl, where dl is here. Where dl is here. dl is here. So we have turn on the angle d phi. P. P is the first letter of precession. Precession is rotation of axis of rotation. So in this case we have that this rotation of angular momentum will be signed like this. So this is the direction of precession. Direction of precession, or direction of angular velocity of rotation of axis of rotation. So in this case, we have that according to this picture, dl is equal to L multiplied by d phi p. And from here we have that m is equal to dl by time, and this is equal to L d phi p by time, and this will be L multiplied by omega p, and this will be if we remember if we remember this formula. If you remember this formula, we can write that this will be I omega p omega. Okay, do you have any questions about this? No questions. No questions. So I'll clean this. From my screen. I'll clean this, and we have that moment of gyroscopic forces. M is moment of gyroscopic forces. It can be calculated can be calculated with this formula. With this formula, and it can also be written. It can also be written in vector form. It can also be written in vector form. It can also be written in vector form. Vector form, we will have that m is equal to right omega p L, and this is equal to I omega p multiplied by omega multiplied by omega multiplied by omega. Moment of gyroscopic forces. Moment of gyroscopic forces. Gyroscopic forces try to prevent us from changing of orientation of axis of rotation. So if we try to change orientation of axis of rotation, these gyroscopic forces will occur, and they will try to prevent us to prevent axis from changing its orientation in space. Okay, and what is the next? The next step is to to consider, or is to learn work of moment of force, work of torque in case of rotational motion around fixed axis. So let's have a look at this axis. This fixed axis, z fixed axis z. In this here we have a radius vector r. Radius vector r, and let's imagine that we have rotation. The angle d phi is infinitely small. Increase or displacement vector is d r. Displacement vector is dr. Displacement vector is dr, and this is angular velocity. This is a right angle, and here what can we say about work? Work over force in this case, dA is equal to F multiplied by dr, and this will be modulus of F. modulus of dr multiplied by cosine of angle between f and dr. Cosine of angle between f and dr. And this will be equal. This will be equal to f perpendicular. What is f perpendicular? As you can remember from our previous lecture, f perpendicular is a vector that is perpendicular to the r, and f perpendicular is perpendicular to omega. So this will be multiple by modulus of dr, and from here, from the picture, we have that modulus of dr is equal to r multiplied by d phi. But this product is equal to modulus of torque related to an axis. Related to an axis. Okay, and from here we can obtain work of at work of a torque related to an axis. Work of a torque related to an axis. It can be calculated with quite simple formula. Integral of this. Integral of this. Integral of this. Okay, do you have any questions? No questions. No questions. Okay. Okay. And what about kinetic energy? What about kinetic energy? If there is no rotation, kinetic energy can be calculated with a simple formula. If there is no rotation, kinetic energy will be m squared v divided by 2. If there is no rotation, but what will be in a case of rotation around the fixed axis? In the case of rotation around the fixed axis, in this case, we have to consider a material system or a rigid body as a sum of material points with different velocities. So in this case, we have to consider kinetic energy like this as this sum, but it is not useful. It is not useful. So let's make this formula simpler. Modulus of velocity, as you know from kinematics, is equal to omega r ri. Omega ri. And we can use this here, and it will be sum of mi ri to the power of 2 omega divided by 2 and let's remember about a moment of inertia. Let's remember about moment of inertia. From here we have that it will be omega squared divided by 2. So we have obtained kinetic energy of kinetic energy in case of rotational motion around a fixed axis. Kinetic energy in a case of rotational motion around a fixed axis. Around a fixed axis. Around the fixed axis. So in this case, we have that kinetic energy is equal to this. So it is much more convenient to use this formula instead of calculation of this sum. Instead of calculation of this sum. So this is useful formula, and it is also ready to use for us. And as the last for today is kinetic energy of rigid body in planar motion. Planar motion. What is planar motion? Planar motion is a combination of a simple motion and rotational motion. Simple motion and rotational. So kinetic energy of rigid body in planar motion. In planar motion. Planar motion. Kinetic energy in this case is equal to m multiplied by velocity v0. V0 is velocity of center of mass, mass multiplied by squared velocity of center of mass, and plus I0. I0 is moment of inertia related to the axis that passes through center of mass. Passes through through center of mass. Divided by 2. Divided by 2. Divided by 2. Okay, so that's enough for today. That's enough for today. And so do you have any questions? No questions. Okay, in this case, thank you for your attention, and I hope to meet you tomorrow.